A ball is thrown horizontally from the top of a 60.0 meter building and lands 100.0 meter from the base of the building. Ignore air resistance. How long is the ball in the air? All right, let's start by sketching the building. So we have this building. This is the ground level. Okay. All right, so if this is the top of the building and the ball is thrown horizontally with a velocity v naught in the x direction, and the horizontal velocity is always the same, so this is going to be v sub x. What about the y component? Because it was thrown horizontally, the initial velocity in the y direction is equal to 0. And the height of the building is h, but if you measure it from the reference point at the top of the building, this will be delta y. All right, so what values are given? We are given delta y. If our reference is the top of the building, then delta y is going to be minus or negative 60.0 meters. Okay, so the trajectory of the ball is going to be something like this. And now we were told that the distance from the base of the building to where it lands is delta x. And we know delta x is equal to 100 meters. And we are ignoring air resistance. So now A is asking how long the ball was in air, t. All right, so from kinematics we know that delta y is equal to v naught in the y direction times time plus half gt squared. Because the initial velocity is 0, we know delta y equals to half gt squared. So if you rearrange the equation to solve for t, you multiply both sides by 2, divide by g, and then find the square root. Yields t equals to 2 times delta y over t. Let's plug in the numbers. 2 times negative 60.0 meter divided by negative 9.80 meter per second squared, the gravitational acceleration. G is a known value, approximately equal to average of negative 9.80 meters per second squared. And this is equal to 3.5 seconds. B. What must have been the initial horizontal component of the velocity? We are asked to find v naught in the x direction. And we know that the displacement delta x is equal to the average velocity, which is constant in this case because the velocity in the horizontal direction is not changing, therefore it remains constant. So multiply that by the time t. All right, and if you rearrange this to find for t, for v naught x, v naught x is going to be delta x over time. We have those values, so just plug in the numbers. So v naught in the x direction, whether it's initial or anywhere within in the horizontal direction, is going to be constant, and that's 100 meters divided by the time the ball was in air, which is calculated in A to be 3.5 seconds. That's equal to 28.6 meters per second. All right. C. What is the vertical component of the velocity just before the ball hits the ground? So you're asked to find V final in the y direction. And V final in the y direction is equal to V naught y initial plus GT. If in the y direction final, 0 plus negative 9.80 meters per second squared times the time, which is 3.5 seconds. That's equal to negative 34.3 meters per second. And D, what is the velocity of the ball just before it hits the ground? So I've asked to find V final. And the V final is going to be something like this. This will be final direction, and this will be the magnitude, V final. So the V final has both X and Y components. Okay, so V final is equal to square root of the X component squared VF in the Y direction squared. The X component is always constant in this case, therefore VF is equal to square root of Vx was calculated in B to be 28.6 meters per second. Square it plus, and the Y component was calculated in C to be negative 34.3 meters per second. Square it. That will be the magnitude. That's equal to 44.7 meters per second. That will be the magnitude, final velocity in magnitude. And the direction theta f is tan inverse of the vertical component to the horizontal component. The vertical component Vfy over Vx, tan inverse of negative 34.3 over 28.6 meters per second, goes with meters per second. And that will be the direction. That's equal to minus 50.2 degrees.